mistake in the first video, so I'm going to try to fix it in the second video. A year goes by and I forget one little detail. It happens. Okay, so in case you don't remember me from last fall in the very beginning, it's been a while since I've seen this class. I was off teaching grad class, so I didn't spend as much time with the sophomores, more the juniors and seniors. But I'm done with that class now, so I'm back to work with you guys in the two sophomore classes, 2004 and 2003. And happy to be back with you to do the wind tunnel testing. This is one of our key features of our program. It's good that you're already familiar with the wind tunnel from last semester's testing, and this will also build upon that experience and add in some more interesting models for you to test. So what we're going to be doing is we're going to have all the groups in this class test 3 different models. We have 2 F-16 models and 1 787 model. The first F-16 model that we're going to have a third of the class roughly test is the clean model. So we call it the clean model because it doesn't have any missiles or tanks underneath it that create extra drag. So we'll compare that with another third of the class that's going to test the actual F-16 model. This is just a kit that you can buy off the shelf, any standard airplane kit that we then modified, put a cylinder in the back so that we can put it on our sting balance to measure lift, drag, and pitching moment. So this dirty model, as we call it, has the missiles and the fuel tanks underneath it for the extra drag. Then lastly, the last groups, the last third of the class, we'll be testing our new and exciting 787 3D printed model that we printed from a company called Shapeways. We printed it outside of the 3D printers available here because we needed greater precision for some of these details. So that was done outside. It cost about $75 to make this model, so it's not too expensive, and it is something we hope that groups can do in the future, especially senior design groups. So this 787 clean model, or 787 clean model will be tested by a third of the class. We also have another model with the flaps deployed down, but we had some issues with this model, and so this one's not going to be ready for testing, and we may have to remake some. So this one is one you can look at for comparison, but we will not be testing it. All right. For the models, we have foam blocks that we use to set the model into place. When you come in to test, the F-16 model will already be, or the 787 model will already be installed on the sting balance. You won't have to worry about that. The reason being, each time we install the model on, it can get placed in a slightly different position. It might be a little bit further back or a little bit further forward. By fractions of a millimeter make a difference. And then all the data is kind of shifted. And so it makes a little more data error than really is necessary. So in order to keep things consistent, we're going to keep the model installed for all the groups that test, and then switch models and keep it the same for all those groups, and then switch to the third model and keep all those installed. The foam block is used when we install the model on the sting to make sure that it's level in roll. So we look at this level bubble here to make sure that that's level. What you will be using the foam block for is to set your zero angle of attack. So this level bubble on top is the one that you want to watch when you set zero angle of attack so that you know the plane is level. Okay? I'm also going to take the plane off just for today during the demo so that you can see what the sting balance looks like. So the new accessory to this spring is the sting balance. This is a cylinder that has inside this protective sleeve strain gauges on the top and bottom of the cutout sections of the cylinder to measure the stretching and compressing of the material in this cylinder. That can then be calibrated to how much force was applied to the sting. So when we press on this sting balance, it can measure how much force I'm pressing on to it. It is a 3-axis sting. It can measure axial, normal, and pitching moment. The axial direction is when forces are pressed back axial along the sting balance.
That's what I'm trying to get.
The normal is going to be perpendicular in this direction to the sting balance. And then the pitching moment is, by right-hand rule, a pitching moment upwards in this direction. So if it pitches the nose of the airplane up, that's considered positive pitching moment. If it pitches the nose of the airplane down, that's considered negative pitching moment. Okay? Axial positive is considered this direction because we use it for relating to drag. At zero angle of attack, these axes of normal and axial are lift and drag, but only at zero angle of attack. As I change angle of attack, these axes move with the balance. So now these are no longer measuring lift and drag. But you can relate those through the sine and cosine of the angle of attack. So we have that available. We could make you derive it, and in fact you should derive it, but we also give you the answer so you can check yourself to make sure you don't make a mistake. And that's listed on page 3 of your handout. It's available on D2L if you want to start looking at it later today in preparation for testing next week or between now and then. So this gives you your equations for normal force, angle of attack, and axial force, and how to relate that to lift and drag. Another important thing to note when you come in to test is to make sure that the sting balance is configured to measure lift and not side force. So there's a note here, side force and lift force with arrows. There's a pin right here that rotates. That pin can rotate 90 degrees. So if the pin is facing towards you, which is what this arrow indicates, if it's facing you, that's correct. That's going to measure lift force. If this pin is rotated away from you, then it's going to be measuring side perpendicular force, not lift force. So that's for other purposes, other tests that we don't need for this class. Okay? This pin orientation is secured with a screw on the back, and we've added a lock washer to help keep that in place. But if that gets loosened up over time, keep an eye on that and let Rachel or myself or Bobby know if that comes loose and that pin starts to rotate. It should be secure. So just double check that when you come in. All right. Then when we install the model, as I mentioned, it's important that the installation be placed correctly onto the sting balance. And I always rotate the model, just so you know how I do this. You won't have to do this. But it's important that we get our set screw in the flat area, which is the measuring transmission of forces area for the sting balance. There's a little ridge where this diameter is reduced. If the set screw is setting on that ridge, the model can actually kind of teeter-totter on that ridge. And that causes some problems in our data when we see that. So we make sure that the model is completely cleared, the area where the diameter is reduced, and then we secure the set screw in order to transmit the forces from the plane to the sting balance. Then we use the foam block in order to set our 0 roll angle first. So I'll set this to 0 roll angle with the front level. Sorry if my back is turned and you can't see that. And then we tighten that down. Usually takes a few tries to get that set just right. So I move it after I tighten it. And now it's set. If you want to verify, it also works well to look from the top down. You can get a better view of the level since the top of the wind tunnel is clear. So I'm happy with that position. Now I can use the level block just as you're going to use it when you come in to test to set the top level to 0 for my 0 angle of attack. In the past, we used to try to balance a level or try to put a level on the back of the sting. Wasn't very accurate. This is a nice machined surface that fits specifically to our F-16 models. So this one, that's kind of a trapezoid shape, is used for the 2 F-16 models. Both the dirty and the clean use the same foam block. For the 787, this one has a foam block with feet that go in front of the wings. So make sure it's installed that way and not backwards like this. So it's supposed to fit like that. And then it has a 2-dimensional level bubble on top to make sure that everything's level in both roll and pitch. Okay? So you'll be using that if you're testing the 787 model. Make sure that the Allen wrenches get back in the foam block. They don't get lost or dropped on the floor, so we don't have to buy replacements. And make sure that you don't leave them in the wind tunnel so they don't get sucked into the fan blades and cause damage.
Has that happened before?
Luckily, no. I always warn everybody, and it's never happened, thankfully. I hope it never does. All right, now we're ready to load up the VI. So we'll go to your class folder. You should be pretty familiar with this. Under courses, spring 2017, 2004 class, and the last folder is our wind tunnel. We'll put a copy of the lab document that was just updated yesterday into this folder down from D2L. The one on D2L is good. There's also some tech documents that you'll use in the data reduction. And the last link is the link to our wind tunnel 2016, which is our latest version of the VI, which has just been updated even as last fall. So this will come up. I saved the defaults and changed them from the 3111 class. They were using 500 samples to save, and you're going to use 20 samples, so we've changed that to the default, but you should double check to make sure that's still set correctly. And then we'll go ahead and run the VI. It's going to ask you where you want to save your data, so save it to whoever's logged in on their Z folder, and then you'll be sharing that with not only everyone in your group, but everyone in the class. So there's quite a bit of responsibility for you as a group to take good data, and don't be lax about it. This is a good point to test your attention to detail and making sure that you get everything done, because your whole class is depending on you for taking data. It's also important that you follow the naming convention. There's a naming convention given on page 5, about in the middle. Use all capitals so everybody is consistent, and also call it the model. We'll have a naming convention for that. Clean, dirty, and 787. Underscore, and then a capital G for group, and then your group number. 2-digit group number. If you're group 1 or 2 or 9, anywhere in there, you need to put a 0 in front of it. If you're 10, 11, 12, that's not a problem. And then .csv. It's going to make your life and everyone in the class's life a lot easier if you follow this naming convention very carefully. That way, when you load all of these 36 or so data files into MATLAB, you can easily do a load command that just indexes the group number. Done, easy. If it doesn't follow the naming convention, then that load statement doesn't work and you have to do it manually, and that's horribly painful. So it'll make everyone's life easier if you follow that. So I'm going to call this capital clean. Get my caps lock on. There we go. Clean group 01.csv, just for example. Actually, I already did 01, so I'll do 02, just for one. Okay, then you should hear the wind tunnel start up. That's a good sign that all the power switches are on. The power switches will be likely turned on before you get here because the steam balance takes about 20 minutes to warm up and reach steady state. So those strain gauges can warm up. So lab assistants and myself will often come in and turn everything on ahead of time. But it's up to you to also double check that all the switches are in the right position. There's an emergency stop button here for stopping the wind tunnel in a problem situation. That should be rotated and in the out position in order to run any voltages to the fan inverter. Otherwise you won't hear that humming sound turn on. You also need to make sure that this power button is turned on here in the panel. That controls the power to our pressure transducers so we can get airspeed. Need to have the SCXI box turned on here with this green LED showing. That's going to get all of your sensor data. Our potentiometer for angle of attack, our pressure transducers for airspeed, and our sting balance for lift, drag, and pitching moment. All go through this box. Yes?
Will we have to calculate the wind speed on our own, or will that be given to us?
That will be given to you from the pressure and calibrated to airspeed on the VI. And you will get both columns of data so you can see that. You'll get a column of data for the pressure from the pitot probe, which is static minus dynamic, and then you will also get the velocity that was calculated using the density for today. All of that is calculated and written to the data file. Good question. You also need to turn this power supply down here on. That's an easy one to forget because it's hidden. Make sure that's on. You'll know that's on when the overhead lights are on, so we can see a little bit better in here, but it also provides necessary power to the sensors. Last one is to make sure that the big 440 volt switch on the wall is turned in the up position so that you can run the high voltages to the fan inverter and run the wind tunnel. Okay. None of these settings you should need to change. These are all defaults. Double check that you're taking 20 samples per data set. The sample rate is fixed. That cannot be changed, but it's displayed for you here. You take data at 500 samples per second. And let's start from the different tabs. We have 3 different tabs to go through. You're familiar with the pressures tab. That's the one you used last fall. That should look familiar. But you haven't used yet the forces or the angle of attack much. The angle of attack used last year, you had to input a manual input for where you had twisted and set the pressure tapped airfoil. Now that's changed to sting balance reading. So what's written to the data file is what's shown on the graph and the display for the angle of attack that's taken from this potentiometer. So we have this zeroed from our level, but when we start up all of our sensors, they don't start up at 0. They have some voltage offset, and sometimes it can be very significant, especially in the angle of attack. It starts out at such a high voltage that it's equivalent to 178 degrees. But that's not a problem. The potentiometer just measures differences in angles. We as the testers have to decide what is a reference to start that from. So we're going to define this as our 0 angle of attack from the level, and then we're going to 0 our angle. That happens instantaneously. The software just subtracts the number out from here on out, so you don't have to do the subtraction yourself. So it's quick and easy. You see that update to 0. Okay? Then we want to go to our forces tab. Our forces tab shows our normal force is the white line, axial is the red line, pitching moment is the green line. So those also come up with different values when we start. Due to offsets in the strain gauges not being perfectly matched, they're not exactly the same resistance, and also the weight of the plane itself. So we take that and zero the forces in moments. Make sure you do that at zero angle of attack. It's important to zero those forces when you are level. And it's going to do a weight for you. It goes inside the SCXI box and turns internal potentiometers. They're electrically controlled to adjust the strain gauge resistance values to match. So that's why it takes time.
So if you tap that thing on the nose right now, you mess everything up.
Correct. Yes. Or if you decided to move the angle of attack, that would also mess up your zero. So that would be bad. So it takes about 30, that counted to 33 seconds, and then that's completed, so it's not too bad. It seems like a long time, but it really isn't. And now you can see all those forces have been set to zero. If you don't want to have to look at all these offsets, you can right-click on the graph. I like to clear the chart, fourth one down. And now I can really zoom in and see how much tiny bit of noise, about 0.02 newtons of noise on our axial and normal force. And the normal force isn't quite perfectly to zero. That's as close as we can get it through the precision of our devices, which is still very good. The steam balance itself is extremely sensitive. It can measure very small forces. You can see we're down to 3 decimal places of newtons. That's very small, millinewtons. So because of that, we also need to measure these very small forces because drag force by design is supposed to be very small. We're trying to minimize our drag. So we're trying to measure a really small force to begin with. Lift force is a little easier to measure. We're trying to maximize lift. So the lift balance can go up to, the normal forces can go up to 111 newtons max. The axial can go up to 44. The reason why these are odd numbers is it's an English-made, United States-made, I should say, company, so everything is in pounds and we convert it to newtons. All right, so if I press directly back in this direction, I can impart an axial force, and you'll see the red line change. I also twisted it a little bit, so I got a tiny bit of normal force. I can also check to make sure that the normal force is working by pressing up on the plane. I can get my normal forces. Then to get pitching moments a little bit are difficult to see, but if I impart a torque and try to pitch up the aircraft while holding the back of it down, it also gives some axial and normal because it's all coupled, but then you can see the pitching moment was me pitching that aircraft nose up. Okay, now we are ready for our pressures tab. This one, the one you're familiar with, also needs to be zeroed. We have our auxiliary pressure. You should remember that from last fall. That is not connected anywhere. It's just shorted to itself. So we just ignore the auxiliary pressure, the white line. Doesn't matter, we don't need it for this testing. And ignore that column of data. You'll also see the scanning valve. This is our general purpose VI. So there'll be a lot of columns of data that you don't need. The scanning valve 16 pressures are all in the data file as well and on the display, but they're not connected to anything. They're just measuring ambient. So we don't care about that. Our pitot probe is measured on the red line, and that is measuring the tip of the pitot probe minus the static ring, which is a ½ an inch back. So that measures the total minus the static, which is our dynamic pressure, which we can directly relate through Bernoulli's to velocity. Our density is displayed here using our atmospheric temperature and pressure measurements, which are inside this box. So that measures the room's temperature and pressure for today inside our room and gives you our density of about 0.95. So keep an eye on those and make sure that those are reasonable numbers. If they go outside of what you would expect, then something could be wrong with those sensors. So we'll go ahead and zero the airspeed and pressures. On this one, it's a countdown because the time to take is deterministic. It always takes 20 seconds. On the other one, it's a count up because it can be slightly variable by a couple seconds. So we'll wait for that to complete. Any questions? Okay. Most of this is getting the setup. A lot of testing and engineering is setup. The testing goes a lot quicker actually than the setup. At this point, you want to double check the test section. Make sure you haven't left any Allen wrenches, pencils, anything inside the test section that could get sucked into the fan blades and cause damage. There's a chicken wire screen at the back to protect the fan blades, but it has pretty big holes in it. So small objects can still get through. If we put a more dense net, like we'll need to do later when you do water rocket testing, it really constricts the flow and we can't get as high of velocities because you're blocking all of that flow. So it's a catch-22 in trying to protect our fan blades but also get good airflow velocities. All right, now we are ready to do our testing. For our angle of attack, it is very important to do your testing in the same fashion for each of the groups. So when we load all these data files in and you're analyzing them, they're all done the same. So all the groups need to start from the negative angle of attack and go positive. Don't reverse the order, going positive to negative. Because then the data files will be different, harder to analyze. But more importantly, aerodynamically, we learned from Dr. Farnsworth, it's important to go from negative angles of attack where the flow is attached and go up to higher angles of attack past stall where flow separation occurs. Because once the flow is separated, it can take longer to reattach. So you actually have some differences and some hysteresis in that. So in wind tunnel testing, you should start from attached flow and then go to separated flow. So that's another reason, even better reason why we're going to go from negative to positive. Some of the groups will do even angles, -8, -6, -4, up to 20. Other groups will do odd angles, -7, -5, -3, etc. And the reason for that is since we can use the economy of a lot of groups, we can get 1 degree increments without taking as much time to test per group. And then share all of the data to fill in the gaps. All right, so we'll take our angle of attack, we'll put it down to our lowest. Let's say we're an odd group. We're going to go from -7. We display 3 decimal places so that you can see the error involved and don't think that it's a perfect measurement. But you're going to want to look for at least 1 0 past the decimal place. It's basically impossible to try to get a second 0. The adjustment of this knob is not going to allow